Section 4.2 is called the addition rule for probability, and we associate this with the word or. And we have seen some of this already. We'll just formalize things a little bit here. So I'm going to repeat our definition of complementary events. So the complement of an event A consists of all outcomes in the sample space that are not part of that event. And we'll be using this notation A with a bar over it to represent the complement of event A. All right, so to introduce the rule for complementary events, let me show you this example. Among clients at a veterinary practice, 25% of clients are cat owners. If we pick a client from the practice at random, what is the probability that the client is not a cat owner? All right, so I'm going to just use this opportunity to go through notation for probability. So let's do the given information. I'll do C for cat. So the probability of picking a cat owner would be 25%. So the probability of picking someone that's not a cat owner would be everybody else. So we know that the entire sample space would represent 100% of clients. So if we remove the probability of being a cat owner, then we will find out the percentage of people that are not. So the percentage would be 75. So I realize this may have been pretty obvious from the start. We kind of talk in percents a lot in the real world. If 25% of people own a cat, the other 75% don't own a cat. So here we're just practicing some notation. So we're covering this rule. So if you take the probability of being part of an event plus the probability of not being a part of it, together you need to get 100%. We will typically be working in decimal, so I'm going to write each of these rules in decimal form. So here I just wrote the rule for complementary events by solving it for the probability of the complement. So that's what we did here. So the probability of not A would be 100% minus the probability of A. All right, so let's do this in decimal, and I'm actually going to write the given here in decimal. So the probability of being a cat owner would be 0.25 in decimal. So the probability of not being a cat owner, so instead of saying 100% would be our sample space, in decimal, that's 1. So one whole group of clients at the practice. And if we remove the probability they're a cat owner, so the same process as before, we're just working in decimal. So that's going to be 0.75. So those two values, instead of saying together they're 100% in decimal, if we add them up, we will get 1. So we'll just fill in the decimal form here. So if you take the probability of an event and add the probability of its complement, that needs to equal 1. And equivalently, in the second version here, the probability then of an event not happening, not A, the complement, instead of 100%, it would be 1 in decimal, is always 1 minus the probability of the event. All right, so we'll be seeing the decimal form of the rule of complements a lot this semester. And then I just did one here as well with a visual, and also to discuss how I'll be doing some fraction work. So for the rest of this video, really, I'm pretty much going to stay in fraction form, just knowing that we could always switch over to decimal or percent, but there'll be a reason I'm doing it this way. So in a certain online computer game, there are 100 players. Of these, 62 are on the A team. The game randomly chooses a player to receive a bonus. Let's find the probability that the player is on the A team and then that the player is not on the A team. And we can practice notation as well. So on my Venn diagram, I'm going to put the 100 players here as our N. So instead of writing number of items in our sample space, I'm just going to make this a little bit shorter and just call it N. So the number of players is 100. And we know that 62 are on the A team. And so it's pretty easy to figure out how many aren't then. 100 minus 62 would leave the other 38 players. But I wanted to kind of introduce, again, the way I'm going to be writing some fraction work moving forward. So the probability, picking somebody on the A team, so that was the given, 62 people out of 100. And we'll just leave it like that. We don't need to reduce. And then let's write down the complement rule. So the rule for complementary events, if you want to know the probability that a player is not on the A team, it's 1 minus the probability that they are on the A team. So this would be 1 minus 62 over 100. And then again, bear with me as I kind of review some fraction work. If you want to subtract two fractions, you'll need a common denominator, in this case, 100. So we would write the 1 as 100 over 100, and then we can subtract the 62 over 100. All right, so the reason for showing you this is when we subtract, we do have that common denominator. So moving forward, I'll be just jumping to this last step where I say that the probability denominators are the same, 100, and then I'll just do my numerators. So 100 minus 62 in the numerator, and that's where 38 over 100 comes from. Sort of mathematically, again, even though we knew it was a little bit obvious here, 62 over 100 and 38 over 100. So those are complements. If you add those two probabilities, you will get 100 over 100, your entire sample space. Okay, so let's go to the actual addition rule for probability. So the addition rule, we'll talk about first using the addition rule for what we call mutually exclusive events. So definition here, events are mutually exclusive if they share no outcomes. So in other words, the intersection of the sets will be 0. So there will be nothing in common in the two events. And so here's an example. If we picked a letter of the alphabet at random, and we let event A that it's a letter found in the word cat, and event B, the letter is found in the word dog, those events are mutually exclusive because they share no letters. If I was doing a Venn diagram, I would write CAT here and then DOG there. There's no letters in common. So that's what a Venn diagram looks like. If two events are mutually exclusive, you're not going to see any overlap in the circles. All right, I'm going to fill this one out for the next rule to introduce then the addition rule. So it says in a basket, we have 20 pieces of fruit, 7 are apples and 5 are bananas. And we're going to pick a fruit at random, and we'll find the probability that the fruit is an apple or a banana. In other words, we're going to find the probability of A union B. So we had this language before. I'm going to go ahead and do my Venn diagram. So N, the sample space, would consist of 20 pieces of fruit. I'll let this circle be the apple circle, 7 apples. And then the banana circle, 5 bananas. So of course, a fruit can't be both of those, right? You either have to be an apple or a banana. There wouldn't be any possibility a fruit is both of those things. So they're mutually exclusive groups, a pile of apples, a pile of bananas. And I can see their total 7 plus 5 is 12. We still need 20 pieces of fruit in the basket. So that will leave 20 pieces of fruit minus 12. We still have 8 pieces of fruit to go. So we've got 8 pieces that are not an apple, and they're also not a banana. All right. So here is the addition rule, and we recognize to use it when we see the word or. So the probability of getting an apple or a banana. So it's pretty straightforward. We just take the probability of getting an apple plus the probability of getting a banana. So in other words, it's a union. So the denominator for both of those probabilities will be 20. So that's why I showed you above. I'm just going to write the 20 once because we know we'll have that common denominator. So basically, we're just doing union. So we're taking all of the apples, so 7. There's a 7 out of 20 chance of getting an apple, plus banana, 5 of them, so 5. So there's a 12 and 20 chance that you're either going to get an apple or a banana. All right, hopefully still pretty simple. So or is union. We know when we see or, we'll be doing adding because we're combining, we're doing the union of the two groups. All right, I'm just going to remind you here then intersection, because the events are mutually exclusive. If we're asked to find the probability that the fruit we pick is an apple and it's a banana, right? So and means you have to be both. So and would mean the fruit that are common to both. And again, you can't be an apple and a banana at the same time. Makes no sense, right? You had to be one or the other. So the probability of A and B is 0. And that's what makes the events mutually exclusive. All right, and then next what we'll do is see how to modify this rule if the two events are not mutually exclusive, meaning they do share outcomes.